Hello everyone, once again welcome to the channel. Today we are going to study complex integration. Before jumping into complex integration, let us recollect the idea of a line integral. So let's find out what do you mean by a line integral. If we have a variable x and if we have another function f of x which is depending upon this variable x, then we write the line integral a to b f of x dx. Here a and b are the starting and the ending points of this line integral. Similar to this, if we have a complex variable z which is actually a function of both x and y, then we also have a complex function f of z. Then we can write the complex integration similar to this form as integral a to b f of z dz. The difference is that in this particular example, this a and b are actually the points in x-axis, but here a and b are the points in the complex plane. I think you got my idea. Now let us find how we can solve the integrals of complex variables. Now we already know that we can write z, the complex number or the complex function, in the form x plus iy, and the complex function f of z is of the form u of xy plus I into v of iota into v of x y. Here u and v are complex functions and z is the complex variable which consists of this x and y variables. Now we can write this z, we know that z is equal to x plus iy, then obviously we can find the differential value dz is equal to dx plus I or iota dy. We can use this result to evaluate this integral. Okay, now let us find how we can find these kind of integrals. Now we can move on to another point known as contours or contour integrals. Contour integration is a form of integral which involves this complex function, but the difference is that the starting and ending points of the limiting values are the same, or simply a closed complex integral can be renamed as a contour integral. That is, we know that integral a to b f of z dz is the normal representation of a complex integral, but when a and b coincides into a single point, then this will become a closed integral f of z dz, where this closed integral represents a contour c. We will encounter different types of contours and different types of applications of contours in the following classes. So I hope you all got my point of the basic idea of complex integration and contour integral. Now let us move on to the evaluation process of complex integrals. So now we have to find a way to evaluation of complex integrals. This can easily be classified or is easily be understood by following some steps. The first step is that before jumping into the solution, first we have to know in which type or what are the ways in which this contour integration can be applied to a question. So basically a complex function is given, say for example f of z is given, and also in some cases they will be specifically mentioned as the contour. The contour is sometimes specifically mentioned, sometimes it is represented as graphs or sometimes some equations. For example, there may be questions asked in the form that evaluate a particular integral over a curve y is equal to x square or something like that. Here we have the correspondence, or we have some connection between the two independent variables x and y to evaluate our integral. So, either sometimes it is just represented as something like this: O, A, B, C, and we are asked to find the complex integral f of z over this closed contour O, A, B, C. So, sometimes these kind of graphical representation are given, or sometimes these kind of relations are given. In either way, we have to integrate our complex function over the contour or over the complex integral. So, now moving on to the steps. Okay. Now, the first step is that we know that f of z is given. This is given as something like z square or z bar the whole cube or something like that. We have to substitute. The first step is that we have to substitute z is equal to x plus iota y. Then what will be the value of z bar? Z bar is nothing but x minus iota y. So, in similar way, we have to substitute these values, x and y values, instead of z. That is the first step. In the second step, we have to find the differential value of z, because we know that the contour integration is something like this, or the complex integration is something like this: f of z dz. We know about the f of z from the given expression, something like this, and we have to find the dz values also, because we are substituting x and y instead of this z, so that we have to substitute dx and dy instead of dz also. In the second step, we are substituting dz is equal to dx plus I dy. This is directly derived from this expression z is equal to x plus iota y. Now, the third step is substitute the variable, that is, for example, if z square is given, then substitute for z square in this expression. That is, for example, if we take z square as the function, then substitute x plus iota y the whole square or something like that. Now, we have to use in the fourth step, we either want to use the graph, or the expression to find the integral value. That is, for example, if it is given that evaluate f of z is equal to z square over the integral y is equal to x square, then in this case, in the first step, we have to put z is equal to x plus iy and dz is equal to dx plus I dy. In the third step, we have to substitute for this value z square, that is, f of z is equal to, instead of z square, we have to substitute x plus iota y the whole square. And in the next step, we have to substitute this value y is equal to x square instead of this y square value here. That is, we can rewrite f of z is equal to x plus iota into, instead of y, we have to substitute x square the whole square. Similarly, in the value of dz also, we have to substitute dx plus what is the value of dy from here? Dy is equal to 2x into dy equal to 2x dx. Substitute the value for dy as 2x into dx, that is dx plus iota into 2x into dx. Now, we can substitute all these to our integral, that is integral something like this. If curve is given or the contour is given, we can easily substitute these two values, substituting for f of z as well as dz, and we can convert the entire integral into a single function, and hence we can evaluate the particular integral of the given function. I think every one of you got my point. Sometimes we can separate the integral, that is, we can separate it into two parts. One is having x values and one is having y value, or sometimes if these relations are given, something like y is equal to x square relations are given, then we can completely convert it into a single variable integral, that is f of x dx in that form. So these are the steps for integrating a complex function over the contour integral. I hope every one of you got my point. Okay, now we can solve some problems. Let's try to solve the first problem. Evaluate integral 0 to 2 plus I z bar the whole square dz along the real axis from z is equal to 0 to z is equal to 2, and then along a line parallel to y axis from z is equal to 2 to z is equal to 2 plus I. If we look into the graph given, that is starting from O, first move up to A through the x axis or the real axis from 0 to 2, and then move upward along the parallel direction to the y axis up to 1. That is why this point is nothing but 2, 1, that is represented as 2 plus I. You know that. So in order to evaluate the integral, already given that f of z is equal to z bar the whole square. The first step is that we have to substitute z is equal to x plus iy and dz is equal to dx plus I dy. In the third step, we have to substitute for f of z, that is z bar is nothing but x minus z bar is equal to x minus iota y the whole square, and dz is equal to what? Same value. Now in order to substitute for this, we have to find the total integral, that is integral from 0 to 2 plus I f of z is equal to x minus iota y the whole square into dx plus iota dy. This whole integral can be split up into two parts, that is from O to A and from A to B. So I am splitting this integral as integral OA. In this range, what will be the value? Here along OA, so first we can write as along OA, x varies from 0 to 2 and y is equal to 0. So since y is equal to 0, which implies that dy should be equal to 0, and we have only want to solve the values for x variable only, because this is only varying in x direction. In y direction its value is 0 and its change is also 0. So y is equal to 0 and the change dy is equal to 0. So we only want to evaluate this x square into dx term only. Similarly along AB, here x is equal to 2 because it is from starting from this point up to this point. So x is equal to 2, we know that, but dx is equal to 0 because there is no change in x direction, only change are in y direction. But in y direction it changes from 0 to 1, and here also dy is non-zero. We have to evaluate that integral, that is I times minus I y, that is we have to expand this, and x minus iota y the whole square, we have to expand it and find the y terms and substitute for that. So we can solve this as integral OA. In OA region, what will be the value of y? It is 0. So we can simply write it as x square dx minus plus integral AB x minus iota y. Here x is equal to 2. So 2 minus iota y the whole square into dx is 0. So we only want to take the term I dy. So this is the final value of the given integral. So now we can evaluate it. In OA the variable is only x, so we have to consider the limit of x from the starting point to the final point, that is it is given by integral x is varying in the OA region from 0 to 2, x square dx, plus in AB region the variable is along y direction and it is changing from 0 to 1. Okay, then it is nothing but I can be taken out and we can take the limit from 0 to 1. Remember, we are considering only the y terms because x is constant 2. So, dx is equal to 0. So, this is given by 2 minus iota y the whole square dy. Evaluating this, we will get x cube by 3 to the limit 0 to 2, and integrating this, what will be the result? It is nothing but we can expand it. For simplicity, we can expand it, plus iota into integral 0 to 1 4 minus 4 iy plus I square minus, so minus, it is minus y square dy, which is given by x cube. 2 cube is 8, 8 by 3 plus iota times integration of 4 is 4y minus 4I into y square by 2 minus y cube by 3 to the limit 0 to 1, which is given by 8 by 3 plus iota times 4 minus 1 square is 1, 4 by 2 is 2 minus 2I minus 1 cube is 1 by 3. Solving this, we will get, taking 1 by 3 common and taking LCM, it will be 1 by 3 into 14 plus 11. You can check it. This will be the final result. I hope you got my point. Okay. Now moving on to the second problem. Evaluate the integral c log z dz, where c is the unit circle, mod z equal to 1. In this case, instead of x plus iota y, we have to substitute z is equal to r is raised to I theta, because the logarithm, whenever the logarithmic function is involved, we have to substitute in exponential form, so that this will become mutually complementary. So, in this particular case, mod z is equal to 1, which says that r equal to 1. So, our function will become, or our variable will become z is equal to e raised to iota theta. This is exclusively for unit circle. Then we can find dz is equal to, here the variable is theta, so that we can write it as iota e raised to iota theta d theta. Now, our integral becomes integral c is equal to mod equal to 1, mod z is equal to 1 log of z is equal to e raised to iota theta dz equal to iota e raised to iota theta d theta. This will become, now d theta is the variable and it is varying from 0 to 2 pi, because this is a circle. So, we know that for a circle the theta value will move from 0 to 2 pi. If this was a semicircle, then theta will move from 0 to pi. So, here 0 to 2 pi, this will become iota theta and into iota e raised to iota theta d theta. I square equal to minus 1, which will become minus integral 0 to 2 pi theta e raised to iota theta d theta. This can be evaluated using UV method as integral 0 to 2 pi, that is minus, we can integrate it as u into integral v, that is theta into e raised to iota theta by iota to the limit 0 to 2 pi minus integral of 0 to 2 pi, derivative of theta is 1 into e raised to iota theta by iota d theta. Now, we know that 1 by I is minus I, we can substitute back, and giving the upper limit it will give 2 pi I and lower limit will go to 0. So, we can write it as minus and then if we substitute for the value of 2 pi, the upper limit and the lower limit, we will get if we substitute for upper limit, we will get 2 pi by I, which is actually equal to minus 2 pi I, and minus of, integrating again, what will be the result? It will be e raised to iota theta by again ni, that will become a plus value, plus e raised to iota theta to the limit 0 to 2 pi. So, if we substitute e raised to 2 pi I, that will be 1, minus e raised to 0 is also 1. So, this term will cancel out, and the final answer is equal to plus minus minus plus, that is 2 pi I. Thus, this integral c log z dz, where mod is equal to 1, mod z is equal to 1 is the contour, then the result will be 2 pi I. I hope you got the idea. Okay. Now, let us move on to some other theorems. The first one of it is Cauchy's integral theorem. So far we have discussed how to solve the contour integration, but sometimes the complex function is so difficult such that it will take much more time to solve in conventional methods. So, in special cases we can approximate some results into it, hence our mathematical process become much more easy. Such a way is called as Cauchy's integral theorem. Here we have a function f of z, and we take a contour, a closed contour. That contour should be simple. If you try to understand the types of contours, there are different types of contours available: simple contour, connected contours, etc., etc. So, now if we have a simple closed curve C, and if we have a function f of z which is completely analytic within that particular contour C, not only within the region but also in the boundary of the contour C, if the function is analytic, then we can simply find the contour integration, that is integral C f of z dz will become 0. So, this is very useful if we consider these kind of functions f of z and these kind of contours, and if we try to find the complex integration. Another easy way to identify whether that integral becomes 0 or not is that if we have no poles within the contour, say if we have a circle, this is the circle and this is our contour C, and if we are taking a complex function f of z inside this contour, say somewhere here at z or wherever it is, and if this function is completely analytic within this contour, then whatever the integral value we are trying to find, everything will be equal to 0. This is very important. So, in other ways, if we cannot find a pole, say we will discuss about poles and other non-analytic terms in the later part of this lecture, but for now, for the sake of knowledge, just for primary knowledge, just consider that pole is somewhere or some point z or z0 at which that function is not analytic. For example, if I have a function f of z is equal to 1 by z, then at z is equal to 0, this function is not defined. So, z is equal to 0 is a pole. I hope you understand my point. A pole is a point where our complex function is not analytic. Whether it is not defined or it is not following the Cauchy-Riemann condition, that is up to the type of problems we are facing, but the definition is that at that point the function is not analytic. So, if we consider a contour C and there is no such poles within this within anywhere inside this contour, then also we can say that this integral will become 0 because all other points are analytic. Okay, this is the verdict of Cauchy's integral theorem. This is very useful in some cases at which the function become more complex, but we can find that there is no poles inside the given contour, then we can directly write the value 0 instead of calculating the whole integral. I think you got my point. Now let us try an example. So find the value of integral c z plus 4 by z square plus 2z plus 5 dz if c is the circle mod z plus 1 equal to 1. Before jumping into the solution, first of all let us recall the idea of the equation of a circle. In complex plane, we can represent equation of a circle as mod z minus z naught equal to r. This is the equation of a circle with z0 as the center of the circle and r is the radius of the circle. So the given circle equation is given by mod z plus 1 equal to 1. So it clearly shows that our point or the center is z0 equal to minus 1 and our radius r is equal to 1. That is why this circle is represented like this. I hope you got the idea. Now let us move on to solving this kind of integral. So if we try to solve this equation using the conventional method of contour integration, it will take much time than anticipated. So let us try to solve it using the Cauchy's integral formula. Cauchy's integral theorem. Cauchy's integral theorem clearly says that if this function f of z is analytic everywhere within this contour, that is this circle, then we can clearly say that this equation or this integral will give 0. In order to check for this condition, we have to first find the poles or the not defined points of this equation or this function. So let us find the function f of z. F of z is given by z plus 4 divided by z square plus 2z plus 5. In order to find the poles, we have to find the not defined points within this function. So the easiest way is to equate the denominator to 0, that is z square plus 2z plus 5 equal to 0. If this becomes 0, then the whole function is not defined and hence we can say that f of z is and not analytic at those points at which this equation will give 0. So we can try to solve this using the quadratic equation formula, that is minus 2 plus or minus root of 4 minus 4 into 4ac means this is 20 divided by 2, z is equal to, which is equal to minus 2 plus or minus root of minus 16 divided by 2, which will give minus 2 plus or minus 4 iota by 2, which is equal to minus 1 plus 2i comma minus 1 minus 2i. These are the two values of z at which this function f of z is not analytic. If we try to check these points in our graph, minus 1 minus 2i is, here it is the minus 1 and here it is the minus 1 minus 1 and somewhere around here we will get minus 1 minus 2, this point. Clear? So the second point is clearly outside our contour. Now again going for the first point, it is minus 1 and this point is minus 1 1, and if we take somewhere around here we will get minus 1 2, which is minus 1 plus 2i, and this point is minus 1 minus 2. Clearly both the 2 points which are non-analytic for the given function are clearly placed outside the contour. So we can apply the Cauchy's integral theorem and hence we can say that integral c z plus 4 by z square plus 2z plus 5 dz equal to 0, because the corresponding 2 points which are non-analytic of this function are placed outside the contour of our consideration. So we can apply the Cauchy's integral theorem. I hope you got the idea. Now let us move on to another point or another equation which may help us to solve a certain kind of contour integrals. It is actually Cauchy's integral formula. Now let us consider the Cauchy's integral formula. We already considered that if there is no non-analytic points within the contour, then the integral, particular integral corresponding to that function will be equal to 0. Contour integration will be 0. But if we want to find the value of that function at a particular point within C, we can use the Cauchy's integral formula. And also if we know the value of that function at that particular point, then we can also find another integral which will be explained soon. So this Cauchy's integral formula is for a point z0 at which our function becomes f of z0, and it is given by 1 by 2 pi I into contours integral over C f of z divided by z minus z0 dz. Say if we know f of z0, that is the value of f of z at z is equal to z0, then we can find the integral over C f of z by z minus z0 dz equal to this 2 pi I into f of z. This is a reverse calculation. I think this is the most important formula than this, because if f of z is equal to given, say f of z is equal to z square, and we are asked to find the value integral C f of z by z minus 2, then how we can find this integral? Just substitute this formula, that is 2 pi I into f of 2, which is equal to 4 into 2 pi I, which is equal to 8 pi I. Similarly, we can find the integrals of this type using Cauchy's integral formula. There is another application for this integral formula, that is we can find the derivatives of function at a point. For example, if we want to find f dash of z0, we can use the modified Cauchy's integral formula for that. Or if we want to find the third derivative of f of z at z is equal to z0, then also we can use the general formula of Cauchy's integral formula in order to find these calculations. Let us find how we can arrive at these kind of general equation. So to find the derivative, this is actually an application for Cauchy's integral formula. To find the derivative of an analytic function, I am giving the most general formula so that we can use it for whatever order of derivation differentiation it is, we can find it. So for an nth order derivative, say fn of z0, it is given by, it is equal to n factorial divided by 2 pi I into integral over C f of z by z minus z0 the whole raised to n plus 1 dz. So if we want to try the first order derivative of a function, how we can find it? That is 1 factorial divided by 2 pi I into integral C f of z by z minus z0 the whole raised to 2 dz. This can also be used in reverse order, that is if we are asked to find integral over C f of z by z minus z0 the whole raised to n dz, what will be the value of this? What will be the value? We can use this equation in reverse order by putting n plus 1 equal to n, or n is equal to, we can lower the derivative value by 1 and we can cross multiply it with these terms. That is, this is simply given by 2 pi I divided by n minus 1 factorial into f n minus 1 of z0. This is the expression for these kind of integrals. So Cauchy's integral formula is a very useful tool to find the contour integration or the derivative in both sense. If we try to find the left hand side, we will get the derivative, and if we try to find the right hand side, we will get that integral. So, this Cauchy's integral formula is very useful to find the contour integration or this kind of derivatives or value of function f of z0 at a point. I think you all got the idea. Okay.